Hello everybody! Today, we would like to present our project on unsupervised phenotyping with the use of tensor factorization. This is our final project as part of our graduate course for CSE6250, Big Data Analytics for Healthcare from the Georgia Institute of Technology. Recent advancements in electronic health record-based systems have resulted in producing data at an unprecedented rate. The complex, growing, high-dimensional data available in AHRs creates great opportunities for machine learning techniques. However, such techniques require dimensionality reduction to achieve efficient processing time and to mitigate the curse of dimensionality. Such records suffer from missing data entries, leading to sparsity that require interpretable results, since the application is critical to patients' health. The ability to derive useful and precise insights from EHRs requires a deeper understanding of the data, intermediary results, configuration parameters, and analysis processes. Hence, the phenotyping approach is used to regroup patients with the same traits. In our work, the phenotype is a triplet of patient demographic, diagnosis, and treatment. Medical data is often presented as large arrays of multidimensional data points. A simple approach for the phenotyping of this data is to cluster each dimension. The problem with this simple approach is that every dimension added also increases the temporal complexity of the algorithm exponentially. As such, the reduction of dimensionality becomes far more crucial than the clustering approach. When working with tensors, one has to consider all relationships between dimensions. But when we have a matrix of the patients and diagnosis dimensions, and another matrix with the patients and medications dimensions, you're losing the relationship between medications and diagnosis. Therefore, tensors are more interpretable than popular dimension reduction techniques such as principal component analysis. Our approach consists of two parts. We will first find and apply a state-of-the-art tensor factorization on a phenotype. We will then predict the missing values from the factorization. In the first part, we implement a sparse ParaFact2, which is a multimodal parallel factor analysis model, and benchmark this against COPA, which is a constrained ParaFact2 for sparse and large datasets. We do this by selecting the phenotype data from the database to generate the ground truth tensor. In the second part, after we've factorized the tensor, we'll be able to find the missing data in the tensor. As our objective is to predict the treatment, we impose the missing values in the treatments and observe how the factorization performs, and then classify these missing values when we reconstruct the entire tensor from factorization. Reconstruction of the tensor is mandatory since we will not be able to perform factorization otherwise. As our database was already sparse, we did not have to perform one-hot encoding. This is similar to making a recommendation system where we want to find the correspondent diseases to symptoms from the tensor factorization. We've used the CMS Data Entrepreneur Synthetic Public Use File Dataset from 2008 to 2010, which consists of 20 patient insurance claims sub-datasets, each containing the following. The beneficiary data contains over 100,000 records of demographic data of each patient, such as their date of birth, the date of death, the race, gender, and past medical diagnosis. The inpatient and outpatient data contain over 60,000 and 790,000 records of insurance claims, with columns such as admission dates, diagnosis, procedures, claim amount, and physician data, respectively. For each of the 20 sub-dataset, we first perform data cleaning and pre-processing, such as to generate the age from the date of birth, aggregate all diagnoses and treatments for each claim into a list, convert string columns into categorical variables, perform missing value treatment, and dropping the redundant columns. We join all three datasets together using the beneficiary ID as a primary key and group all the claims by beneficiary ID so that each patient will have a list of claims for both inpatient and outpatient claims. Finally, we have an ETL script to generate a 3D tensor with the following structure: the list of patients, the list of visits, and a list of diagnoses and treatments. We apply ParaFact on different ranks and choose the best low rank with the best explainability trade-off. By understanding the dimensions on which ParaFact projects, we reconstruct a tensor by eliminating the missing dimensions. We then apply COPA and compare to ParaFact using different metrics such as explained variance, Hamming loss, and mean absolute error. To compare the factorization methods, we look at the norm of the noise associated with each factorization. The factorization with the noise of the smallest norm is theoretically the best. You can look at several different standards to see if there are any differences in performance. On each of the factorizations, you can also modify the rank of the factorization and compare them with each other. This is achieved by the fitting accuracy. We also check if a variable present in the original tensor appears in its factorization of rank. This is achieved by features membership. The goal is to understand why some factorization admit for features in its decomposition than others. With respect to COPA improvement, we've also optimized COPA constraints, that is, finding the optimal combination of constraints for all equivalent ranks. In the COPA paper, they have tested Parafact versus COPA. The difference here is minimal, but COPA has proven to be a better factorization method overall, as shown in our results. Therefore, our work aligns with the results presented in the paper both from an empirical and a theoretical point of view. Another challenge we've faced is the large memory requirements needed for the tensors on the full database. We resolved this by first running a sample of the dataset for rapid prototyping before deploying the full database on a Spark cluster running on Azure's virtual machines. This allowed us to scale over several hundred gigabytes of memory to process the data and perform the analysis. Other algorithms such as streaming Parafact were also considered, however the challenges arose mainly due to the large size of the matrix with sparsity. Moreover, with the translation of the existing code from MATLAB to Python, there were inherent bugs and issues that were unresolved. In conclusion, we further improved the algorithms for COPA and Parafact 2 using nucleus norms and in the experimentation, allowing flexibility of relaxing constraints. We also factorized missing values for prediction. In future, we will plan to implement COPA intensively and improve the original algorithm further with COPA 2. So thank you for viewing our presentation and I hope it has been useful for you. Have a nice day.